Welcome to our last lesson of Electrodynamics. We'll be taking a look at some more questions that you can expect in tests and exams. Now, one of our first questions asks us that in this case we've got a circuit that has an AC source that delivers alternating voltage to an audio frequency to our speaker. So if you take a look at your circuit, you then have in this case a series circuit. Here is your power source, that is an alternating power source. That means the positive and the negative will swap around, and then this is a 15 volt RMS source. Note though that we've got two resistors, one is an 8.2 ohm resistor and the other that of a speaker of 10.4 ohms. They then go on to ask you what is the peak voltage that the source can deliver. Now the word peak here refers to our maximum potential difference that the source then can deliver. So that means our formula of Vrms is equal to Vmax divided by the square root of 2 will be used, and we've got this RMS value to be 15. Thus we will end up having our Vmax is equal to 15 times the square root of 2, which ends up giving us a potential maximum value of 21.21 volts. Note that we do round off to 2 decimal places. Now the next question asks you to calculate, in this case, the average power that can be delivered to the speaker. Note that they're specifically talking about the speaker to which this average power will be delivered. Now we're going to have a few options for using as our power formula. We can either say our potential difference times our current, which is our RMS values, or we can go and use the potential difference squared divided by the resistance, or the current squared times the resistance. Note again that in both cases it must still be the Vrms and the IRMS formula. Now, should we would like to go and calculate the power over the speaker, we need to make use of all the values that is then only applicable to the speaker. Now first off, we've got a resistance, so that means we're either going to use formula 2 or 3 because we're going to be having resistance to work with, and then we can go and calculate the current that will be running through the speaker, because the total current of the circuit, independent of where you measure it, will be the same, seeing that this is a series circuit. You would know that we've got the RMS value here for the potential difference, but that is for the whole circuit combined and does not only go over the speaker. So we're then going to first calculate the current that will be running through the circuit using V is equal to I times R, and we obviously will be using our RMS values for the potential difference, and then that means we'll end up getting the current value also RMS. So from this we're going to say 15 is equal to the current times 10.4, which is the resistance for the speaker, plus the 8.2, which is the resistance of our next resistor in series. Note though, because we calculate the total current, we'll use the total potential difference and the total resistance. That's how come we go and add them up. And our current that we get from this is 0.806. And note that with a few decimal places, we do not round this off yet because this is not my final answer. So together with my current and my resistance, if I want to go and calculate the formula or the power, we're specifically using our last formula over here. And that is average power is equal to the current RMS squared times the resistance. And remember, we're using the whole of that current with all its decimal places squared times the resistance of only the speaker, because that is in this case the power we want to go and calculate, which is 10.4, and that gives me a power of 6.76 watt. The next question asks us, in this case, that alternating current that is generated at power stations do make use of two advantages that these AC transmission over long distance do have for us. Now, if we do have specific AC current, we first off are be able to be making use of our AC current in transformers. And transformers again are those apparatus that help us step up and step down our potential difference. And secondly, seeing that we are able to be making use of our transformers, then it means our transmission of our electricity over long distances can make use of a step-up transformer. That means we'll have a high potential difference, but a low current will then be used to transmit this electricity. and that at the end leads to less of our electrical energy being lost, or rather transferred, to heat energy. Our next question starts off by telling us that lights in most of our households are connected in parallel, as shown in a simplified circuit which we'll take a look at now. Two light bulbs rated 100 watt and 220 volts and 60 watt, also 220 volts, respectively, are connected to an AC source that is an RMS value of 220 volts. So here is our circuit. Note that the fuse in the circuit allows a maximum current of 10 amps. So we've got our potential difference source, which is RMS of 220 volts, and we've got two bulbs connected in parallel to each other, one with a power rating of 100 and the other of 60. Now in the circuit there's also a fuse of 10 amp. Now all that a fuse does, it means basically that it can withstand a current of up to 10 amp. Anything higher than 10 amp will then in this case cause the fuse to blow out and cause a break in the circuit, which would mean that there will be no current able to run through the circuit. Now our first questions concerning this ask us to calculate the peak voltage of the source. So that basically means our maximum voltage, and we do have the RMS voltage. So that means we'll be making use of the formula VRMS is equal to Vmax divided by the square root of 2. Our RMS value is that of 220 volts. And that means we'll multiply with the square root of 2 to end up getting Vmax of 311, rounded off to 2 decimal places, of 1,13 volts. So that's the maximum potential difference that can be delivered, in this case, via our source. The next question asks us that we need to go and calculate the resistance of my 100 watt light bulb when operating, in this case, at optimal conditions. Now note, remember, they are connected in parallel, and that implies that the potential difference across each one of these branches will be the same, and seeing that there's no other resistance in the circuit, it will then be the same as the total potential difference that is delivered here by the circuit power source. So that means 220 volts across the 100 watt and across the 60 watt would be experienced. So we've got a potential difference then of 220 volts. We want to go and calculate the resistance. So V we've got, R we want to go and calculate, and the power we do have. So using these three variables, we can then be making use of a formula that says power is equal to V squared, remember the RMS values, divided by the resistance. Now this average power is given as 100 watt, and our squared 220 volts here divided by the resistance, but do take note that our resistance here are below the line. So it's best to rather take it out from underneath the line and multiply out with it so that it ends up being at the top. So if we multiply out of the resistance on the other side, then we'll divide by the 100 so that we're left with the resistance over there. So it becomes 220 squared divided by 100, and that gives me a final value of 484 ohms. The last question asks us though that we've got an electric iron with a power rating of 2200 watt. It's now connected across points A and B and our original circuit. Explain with the aid of a calculation why it's not advisable. Now here's points A and B. That means that we're going to connect this iron of 2200 watts parallel to the remaining 160 watt bulbs that's already existing there. Now if we want to go and use a calculation to show whether it is advisable or not, we basically want to end up calculating the current, because we've got a fuse that can only take 10 amps of current. That means anything in this case that is higher than 10 amp will end up blowing the fuse, and therefore it's not advisable, because then there will be no current left to run through the circuit. So we are going to calculate first off just the current that will be running through our branch with the 2200 watt iron connected to it. Now let's just quickly take a look as to what we will be using. We would like to go and end up calculating current, and we do have the power as well as the potential difference, because seeing that it's still connected in parallel, it will also receive a potential difference of 220 volts. That ends up having us using the power is equal to VRMS times IRMS. Remember, we must use our RMS values in calculating the average power. And we've got a power of 2200, in this case a potential difference of 220 times the current, and the current then ends up being 10 amps. Now that's 10 amps for just that very last branch. When we're going to consider the total current, note though that we will then adding our last branch, our second last, and the first branch's current. And that must not be greater than 10 amp. But if my very last part of the branch already is 10 amp, and I still need to go and add the other current to it, then we'll end up with a current greater than 10 amp, which will cause this fuse to blow. So therefore it would not be advisable to connect this iron of a 2200 watt rating parallel to the remaining part of the circuit, seeing that it will end up having the fuse to blow, and that will cause a break in the circuit, preventing any current from flowing in it.